Okay, let us continue. In this class, we'll see magnetic field at the center of a loop made of non-uniform wire. Alright, now a wire can be non-uniform in two ways. Let us see two simple cases here. So, first case, you can say the wire is made of same material. Otherwise, let us take the material is different. Okay, the material is different, but the thickness of the wire is same. For example, thickness is same. Okay, now what it means is you can take something like this. Say you have a loop here, right? So you have a loop, right? And we will connect the diametrically opposite points. Okay, we'll connect the diametrically opposite points to a battery. All right, we'll connect it to a electric cell or a battery. Fine. So current starts flowing in this. Fine. Now, if the wire was made of the same material, you know the current I1 and the current I2, it will get, sorry, I2 is this way, right? If the wire is made of same material, then I1 and I2 would be same, and the magnetic field at the center would be 0, right? Now, here what we are doing is half of the loop, say it is made of a different material and the other half is of different material. For example, as given in the book, say this, the first half of the loop, okay, or half of the loop, it is of one material, okay, call it as gold. Okay, so this can be gold. Okay, call it as gold, and the other half of the material, so it can be made of some other material. Let us call it as silver. Okay, let the other half of the material be half of the loop. It is made up of silver, Ag. All right, fine. So this is Au. Right, so that is Au. Right, now what will be the current? What will be the current in both of them? How to identify means, see here, since we have chosen the points where we connect the battery to be diametrically opposite points. Okay, so you can say point 1 and point 2. Okay, point 1 and 2 are diametrically opposite points. Okay, they are diametrically opposite, right? So what you can notice is the length. Okay, the length of the gold wire, okay, and the length of the silver wire, both are equal. Okay, and we have chosen thickness to be the same. Okay, so you can say area of cross section of gold, that is equal to area of cross section of silver. Okay, so this is area of cross section. Area of cross section. Alright, fine. Now, yesterday we have seen a formula on how you can find out the resistance depending on the length, cross section area, and its specific property, right? So it is given by this, R is equal to rho L by A, right? Now, if you try to find out resistance of gold and resistance of silver, okay, you will find that it is equal to, in this particular case, it will be the ratio of resistivity of gold divided by resistivity of silver. Okay, and we know that the resistivity of silver is actually less, right? So silver, it is by far the best conductor of electricity at normal conditions. Okay, if you if you do not consider superconductors, right? Now you can say resistance of silver is less than resistance of gold. Okay, resistance of silver is less than resistance of gold, right? Now if you consider this, say same length, okay, same length, same area of cross section, but resistance in the lower arm, that is the pink line, resistance of that pink line, it is actually less compared to resistance of that's yellow line. So wherever you find less resistance, the current flowing through it will be more. Okay, so you can say, call it as IAG. All right, so the current flowing through AG, let us call it as IAG. Now the current flowing through AU, so let us call it as IAU, right? So naturally what you can find is the current flowing through IG, that is a silver, not Ig, Ag. So Ag will be greater than current flowing through gold, correct? So what will be the magnetic field at the center? Okay, if I try to find out what is the magnetic field at the center, B. Okay, so you can write B is equal to, B is given as mu naught I alpha divided by 4 pi r. Okay, so this is what we have seen, right? Fine. So this is due to an arc. Okay, this is the angle subtended by the arc, right? So if you say magnetic field due to the current flowing in Ag, right? So that you can write it as mu naught I into, now alpha is actually pi radians, whole thing divided by 4 pi r, correct? Yeah, so you will get it as, this is Ag, so this will be mu naught I Ag divided by 4r, right? Now similarly you can write magnetic field due to the current flowing in gold, right? So that will be given as mu naught I Au whole thing divided by 4r, right? So if you compare these two expressions, we find that the magnetic field due to the current flowing in silver, it is more, right? So you can clearly see that BAG is greater than BAU, right? Now what will be the net direction here? You can update in the diagram. See, the magnetic field due to current flowing in gold, right? So it will be this way, right? So if you use your right hand, you will find it is this way. Now magnetic field due to the current flowing in silver, it will be towards you, right? So the net magnetic field, right? So the net magnetic field B, you can write it as BAG minus BAU, and the net magnetic field at the center, okay, if you focus on this, if you focus at the center, it will be towards you. Okay, the net magnetic field is towards you at the center. All right, fine. So what is the magnitude of that? Means, you know, at the center, the vectors BAG and BAU, the magnetic field due to current flowing in silver and gold, right? So they are opposite in direction. So therefore you can say the net magnetic field at center, okay, it is given as BAG minus BAU, right? So therefore you will get it as mu naught divided by 4r times IAG minus IAU. Okay, IAG minus IAU, right? Fine. So this is the result what we get, right? Now if we take a look at the second case, right? So second case, you can say here in the first case we have taken material is different, thickness is the same, right? So in the next case you can take a material is same but the thickness is different. Okay, so you can take that case also. Second case, you can say material is same, okay, but thickness is different. Okay, so that will be the next case. Okay, thickness different, material is same, right? Fine. Now what you can do is again consider a loop. Fine, consider a loop. Now we are connecting the diametrically opposite points to we are connecting the diametrically opposite points to a battery. Okay, so call it as point 1 and 2, same thing just like in the last case. Now we will connect it to a battery. All right, now the net current is I. All right, now what we'll do is one of the arms, right? So you can say half of the loop, right? Half of the loop will make it thick. Okay, so this is actually thicker. Right, this is thicker. So naturally what we'll find is more is the thickness, right? Here if you try to find out the resistance, say I1 is the current flowing through the thicker arm, I2 is the current flowing through the thinner arm, right? So fine, so you can say R, right? Material is same, so R is rho L divided by A. Okay, now if you imagine L of, that is length of the thicker arm and length of the thinner arm, both are same, right? So length of both the arms are same. Length of both the arms is same. Okay, fine. So you can say R is equal to rho L divided by A, right? Now you can say R lower and R upper. Okay, upper arm is thicker one. Okay, so lower arm, right? So if you get the ratio, see for both the arms, what you will notice is that it is made of the same material, so resistivity will be the same. For example, imagine copper, right? So you can say RL as resistivity of copper, length of the copper wire divided by area of cross section. Now upper arm, you will say resistivity of copper, then length of the upper arm, let me write LL here, length of the lower arm, right? So whole thing divided by cross sectional area of upper arm. So here let me write EAL, okay, cross sectional area of lower arm, length of the lower arm, length of the upper arm, cross section area of the upper arm, right? Now if you get the ratio, so what you will find is RL divided by RU, that will be equal to AU divided by AL will get, okay. So you will find out the resistance, right? So the resistance of lower arm is more than the resistance of the upper arm, okay. Resistance of lower arm is more than the resistance of upper arm, okay, because what is that? Cross sectional area of upper arm is greater than cross sectional area of the lower arm, so that is why. So RL is greater than RU, right? Now what does that tell you? More is the resistance. This also implies that more is the resistance, less will be the current in that particular arm. So which arm has more resistance? Upper arm, right? So you can say current in the lower arm, correct? Current in the lower arm will be less than current in the upper arm, all right? So you find more current in the upper arm, all right? Fine. Yeah, from this you can clearly, now you can use your right hand. So magnetic field B due to upper arm, so you can call it as U and L, upper arm and lower arm, right? So BU, you can write it as mu naught I1 divided by 4R, just like from the previous case, right? So mu naught I alpha divided by 4 pi R we will get, okay. So alpha, it is actually pi, you will end up getting this result, right? Now BU, it is actually into the plane of the paper, is it not, if you apply your right hand, right? So yeah, let us call it as IL and IU, okay. So let this be IL, fine. Sorry, this is due to lower arm, right? Yeah, I made a mistake here, so let us change the notation. So let the current flowing through the lower arm, let it be IL, current flowing in the upper arm, let it be IU, okay. Yeah, now I think everything is fine, all right. So yes, so BU, correct. So it is given by mu naught IU divided by 4R, mu naught IU divided by 4R, correct. So it is actually into the plane of the paper, plane of your computer screen, cell phone screen right now. Now BL, it will be given as mu naught IL divided by 4R, right? Now if you use your right hand, it is actually towards you, BL is towards you, right? Now which is having more magnitude? So obviously current in the upper arm will be more than the current in the lower arm, so therefore you can say the net magnetic field, right? Now you can say since IU is greater than IL, BU will be greater than BL, right? So the net magnetic field at center, it can be given as BU minus BL. So that is, you can take out mu naught by 4R common. So then you will be left with IU minus IL, okay. Now the direction is, yeah, the direction is actually into the plane of the paper, fine. So this is the direction, all right. So this is what we have got, fine, all right. Now yeah, moving on to the next topic. Okay, the next topic is magnetic field at the axial point of a current carrying conductor, okay. Right, now you know this already, so let us try to write it again. So say this is the loop, okay, it is in some plane, right? Then we will draw the axis of the loop, say this is the axis of the loop, and say the center is O, all right. Now at point P you are supposed to determine the magnetic field due to the current flowing in this, okay. So if you consider your right hand here, Fine. So we will actually see the magnetic field at that point P. It will actually be this way. Okay, and we have seen that this BP, it is due to the resultant of the magnetic field due to each and every current element, right? So ultimately, vertical components will get cancelled, then horizontal components will get added up, right? So the sum of the horizontal components, okay, so that is what gives rise to this BP. If you add all of them, you'll get BP, right? Fine. So yeah, so let us say this is BP. Fine. Now say the distance OP, okay, the distance OP is actually given by x, right? So let it be x, and say r is the radius, okay, the r is the radius of the loop, right? Then the magnetic field BP, okay, the magnetic field BP, it was actually given by mu naught n I r square whole thing divided by 2 times r square plus x square whole power 3 by 2, correct? So n you can consider as the number of turns, total number of turns which are closely wound. All right, fine. Right, so this is the magnetic field at a point x from the center of the current carrying loop. All right, fine. All right, now what you can do is, let us try to modify this equation a little bit. Okay, so BP, you will get it as mu naught Ni r square whole thing divided by 2 times r square plus x square whole power 3 by 2. Okay, now what we'll do is, we'll multiply and divide by r. Okay, we'll multiply and divide by r, right? So if you multiply and divide by r, so you can actually write it as mu naught Ni r cube, okay, whole thing divided by 2 times, okay, so 2r times r square plus x square whole power 3 by 2. Okay, right. Now if you look at this expression, mu naught Ni by 2r, let us keep it this way. Okay, now this one you can write it as r divided by root of r square plus x square whole cube, isn't it? So you can write it like this. Fine. So it turns out to be mu naught Ni divided by 2r, right? Then r by root of r square plus x square. Okay, now if you remember in the diagram, okay, in the diagram you can actually draw the angle subtended by the ends, okay, or you can say the points, right? Each and every point, right? So just try to see what that point subtends an angle with respect to the line x, that is the line OP, right? So you can take this as the line. Okay, this is the line subtended by each and every point on the circumference, or you can say each and every current element at P with respect to the line OP. So call that angle as some theta. All right, so let that angle be some theta, right? Now we are talking about this theta, right? Now if you write sine theta here, you will observe that you can write it as, now this value here, it will be x square plus r square, right? So sine theta you can write it as r divided by root of x square plus r square. Now we are simply substituting the value here, r divided by root x square plus r square. For that you can write sine theta, correct? So mu naught Ni by 2r multiplied by sine theta whole cube, correct? Now this mu naught Ni by 2r, so what it is actually magnetic field at the center, correct? Magnetic field at the center, magnetic field at the center of a loop having n turns, right? B center into sine cube theta. So this is the magnetic field at an axial point. Okay, and that point, right, at that point it subtends some angle theta, or you can say the angle made by the point. Okay, so if you draw a line from the point to the what is that, current elements, right? So each and every current element, it subtends an angle theta at that point P, right? So that theta is what we have taken here, right? So this is one more way of writing the expression, so remember this. Fine. Now moving on, we can write fine. Now let us try to see the same context, magnetic field at a point, okay, at a point very close to, or you can say at a point close to the loop on the axis, okay, on the axis, right? Now we will take the same expression here. So what we have is the axial magnetic field, it is given as mu naught n I r square whole thing divided by 2 times r square plus x square whole power 3 by 2. Alright, fine. Now what we'll do is we will take this r square common. So in the denominator, mu naught n I r square whole thing divided by 2 r square. Okay, so 2 times r square, then you will get r square divided by, no, this is 1, right? Yeah, so this will be 1 plus x square divided by r square. Okay, then whole power 3 by 2, right? So when you are taking 3 by 2 as the power, now here also you will get the same power 3 by 2, correct? R square whole power 3 by 2 we are actually taking common. Fine, I think you understood that point. Fine, so finally you can write it as mu naught n I r square whole thing divided by 2. Now you have r cube, correct? 2 r cube, then 1 plus x square divided by r square whole power 3 by 2. Alright, now r square and r will be left here. Alright, so you have mu naught n I divided by 2 r. Okay, then mu naught n I divided by 2 r, then this 1 plus x square divided by r square, let us take it to the numerator, then the power will become minus 3 by 2. Alright, now finally you can write it as mu naught n I divided by 2r times, using binomial theorem you can write it as 1 minus 3 by 2 x square divided by r square. Okay, see the derivation, the result is for a point which is close to the loop, that is it is on the axis but it is very close to the loop, that means the center of the loop, right? So here this formula you shouldn't blindly by heart this. Okay, so this is magnetic field at the axis for x much less than r. Okay, so this is valid only if x is much less than r. Okay, so you need to remember this. All right, fine. Okay, now next we'll consider what will be the magnetic field for a far point on the axis. Okay, so magnetic field at a far point on the axis. Okay, right, now you can say B axial is equal to mu naught n I r square divided by 2 times r square plus x square whole power 3 by 2. Then here far point means we are considering this point P to be quite far, so x is much greater than r, will say. Okay, so finally you can easily find this one, so n I r square divided by 2 into, now what this means is if x is much greater than r, you can write r square plus x square is approximately equal to x square itself. Fine, so you can write 2 times x square whole power 3 by 2. Alright, fine, so we'll get it as mu naught n I r square whole thing divided by 2 x cube. Okay, so this is what we get. Now what we'll do is we'll try to write it in a form where you can actually introduce magnetic moment. Okay, so for that what we can do is let us multiply mu naught n I r square divided by 2x cube. Okay, now let us multiply by 2 pi on both sides. You'll understand why. Okay, if you multiply and divide by 2 pi, not on both sides, multiply and divide by 2 pi, so you'll get it as mu naught n I 2 pi r square, okay, whole thing divided by 4 pi x cube. Okay, right, now if you can recall, we write it as mu naught divided by 4 pi, right? Then 2 times n I pi r square whole thing divided by x cube, right? Now if you remember this, now what is pi r square? Pi r square is area of loop. Okay, pi r square is actually the area of the loop, right? Now Ni pi r square, that is Nia, you can write it as magnetic moment of that particular loop having n turns, and current flowing through it is I, right? So mu naught pi 4 pi into 2m divided by x cube, right? So since it is axial magnetic field, so you can introduce vector symbol here. Okay, fine. See, can actually derive this. Okay, you are keeping the equation. Okay, you are keeping this equation in this particular form. So this equation, whatever I have drawn in the box, okay, axial magnetic field. So we know it already, correct? Right. So this was about the magnetic field due to a current carrying loop at the axis. Okay, fine. Yeah, we'll see in the next class. We'll continue in the next class.